Within this part of the course, we are going to see the concept of dependability. Here, we are going only to briefly consider the topic, linking it to the computing infrastructure course. The goal is to provide you the basic tools to support the design and analysis of a computing infrastructure. If you are interested in a more detailed discussion on dependability topic with different viewpoints and different level of abstraction, you can attend the dedicated course Dependable System. This first video wants to introduce the basic concept and terms needed to face the topic. If we want to define the concept of dependability, we can use the official definition, or we can briefly mention that dependability is the ability of a system to deliver its service to the user. Dependability is a general term that includes different properties which are expected from a system. In particular, in this course, we are interested mainly in the concept of reliability, which is the continuity of a correct service, availability, that is the readiness for providing the service, and maintainability, that is related to the reparability of a service. Different devices or applications require different level of those attributes, giving more importance to one of them with respect to the others, depending on the specific use cases. Of course, ideally, it would be better to have all the attributes at the maximum level. However, we know that this is usually not feasible. Let us have a couple of examples. For a cardiac patient with a pacemaker, the ability of a system to continue working without interruption, which is the system reliability, is crucial. Actually, it is a matter of life or death. On the opposite, in automatic teller machines, so on the ATM, the portion of time in which the system is able to deliver its service, and now we're talking about system availability, is an important measure. The ATM can have frequent interruption of a service. However, it will be important also that the time to repair the ATM is short, maximizing when the ATM is available to the citizens. When we want to describe the behavior of an IT infrastructure, we have to consider different interactions and different elements that do not always act in a deterministic way, or they have complex mechanisms that are difficult to be explained at the system level. We can consider as an example the human factor, or the interaction with the environment, or technology-related effects such as the aging of components. This makes dependability, that we'll see in the second part of the course, also performance, two topics that can be described using deterministic laws, but they should be approached using statistical techniques. Let's see how these laws looks like in the context of dependability. To derive the probability of a failure in a system, we have to define the probability density function of that failure, FDT. Given a certain item, the time t, capital T, to the first failure can be described as a non-negative random variable that goes from 0 to plus infinity. The probability density function is not the probability that the failure happens in a certain moment, but it represents its density. This because we are working in the continuous space. To extract the probability of the failure in a certain period dt, we have to integrate the probability density function fdt over that period. Then we have the probability that the failure, so the value of capital T, is between t and t plus dt, where dt was actually the interval of interest. More interesting and a bit more concrete in our direction is the cumulative distribution that can be derived from the probability density function seen in the previous slide. This cumulative distribution is called unreliability and represents the probability of having a failure in an interval between 0 and t. In other words, capital F of t, that is the unreliability, is the probability that the fault, represented by the random variable capital T, is smaller than t. Analytically, the unreliability is the integral between 0 and t of the probability density function f dx in the x. And we know that the probability density function can be derived by its cumulative function capital F applying a derivative steps. As a characteristic of the unreliability function, we have that the unreliability for t equal to 0 is 0, and the unreliability for t that goes to infinity is 1. So which means that the probability of having a fault at t0 is 0, and the probability of having a fault before infinity is 1. From the unreliability function, we can derive the reliability function, that is the probability that the component does not fail in an interval 0 to t, given that the component was working at t equal to 0. The reliability, capital R, is equal to 1 minus the unreliability, and represent, of course, the probability that the fault, so that the random variable capital T, has the value that is larger than t. We have some property of the reliability as for the unreliability, is that the reliability for t that is equal to 0 is 1, and of course that the reliability for t that goes to infinity is 0. As before, the probability density function f dx is equal to minus the derivative of the reliability over dt. If we want to summarize the concept seen up to now, we understood that, considering the time t, the unreliability value is the probability that an item fails before that moment t, while, on the opposite, the reliability is the probability that the same item does not fail before t. Now, the question is how it is possible to compute the reliability or the unreliability. To do so, we have to consider n0 independent and identical elements deployed at time t equal to 0, where all of the items are not failed. Then we let them start working under identical conditions, and we keep track of when a component fails. We consider t1 the time when the first component failed. Then we consider t2 the time at which the second component fails. Then t3 the time at which the third component fails, and so on and so forth, up to tn0, when the last component fails. If we count in each moment the number of components that are still working, so that are at the beginning n0, after t1 is n0 minus 1, after t2 is n0 minus 2, and so on and so forth, up to 0 after t n0 minus after tn0, and we normalize this value with respect to n0, so considering nt the number of elements that are still working after t, the reliability in that moment is n dt over n0. If we consider the value of n0 that goes to infinity, then the empirical function converges to the reliability function R. Of course, we can do also the opposite. If we count the number of components that fails, instead of counting a number of components that did not fail up to that moment, okay, and we again normalize the value with respect to the sites n0, we can find the unreliability function. Let us have a simple example considering a component with reliability 99% when T is equal to 10,000 hours. It means that the probability that the component does not fail in the first 10,000 hours is 0.99. Now, let us consider another component that, with the same functionality of the previous one, and that after 10,000 hours, it has a reliability value equal to 90%. Meaning that the probability that the component does not fail in the first 10,000 hours is 0.9. So that 1 out of 10 components failed before that moment. In this case, we can easily say that the first one is more reliable than the second one, after 10,000 hours. But now, let us put a simple question. What about if we have another component, a third one, that have a reliability value after 20,000 hours equal to 90%? Is this more or less flexible than the first one? For what I know up to now, I can't say anything. And for the moment, I can only answer with the typical engineering answer, that is, it depends. Another important definition is the mean time to failure, MTTF. The mean time to failure of a component is the expected time of the occurrence of the first failure. Given a random variable t representing the time of the failure for the component under analysis, we can derive its average value with the formula that we know from the basic statistics course. Then MTTF, so the mean time to failure, is equal to the integral between 0 and infinity of t multiplied by f in the t. In an empirical way, if we have L0 identical component, 1, 2, 2 and 0, we can calculate the mean time to failure by summing the time of each failure and then dividing by n0. For n0 that goes to infinity, this value converges to the mean time to failure. Interestingly, there is a characteristic of the mean time to failure that is equal to the area under the reliability function curve, which means that the mean time to failure is equal to the integral between 0 and infinity of R, so the reliability function in dt. To derive why this is true, it is we have to simply apply the integration by parts rule starting from the MTTF definition here. The last term we need to define is the failure rate. In the following, we are using lambda to represent the failure rate. and in particular we use lambda t because this function is a function of time. From the failure rate, we can derive the probability of failure for a component by integrating it over a center interval, or by multiplying by the interval if the interval dt is small enough. Lambda t dt is the probability of failure of a component in a certain interval between t and t plus dt, considering that the component was working at the beginning of the interval. We have to pay attention because this is a small difference with respect to the probability density function that we saw before. In fact, the probability density function multiplied by dt is the probability that the component fails within the interval t and t plus dt, considering that it was working at t equal to 0, not at t equal to the beginning of the interval of interest. This equation shows us how the two cases are similar, except that if we consider the failure rate, we have to take into consideration the conditional probability that the event t, so the failure of the component, happens after the value t, so the beginning of the interval. Among the useful formulation for the reliability, we have that lambda t is equal to f dt, so the probability density function, divided by the reliability function. To demonstrate this, we have to start from the probability, from the probability that the component fails in the interval between t and t plus dt, given that it was working at the beginning of the period. So actually, this probability is equal to lambda t in dt. If we express this probability, we can see that this probability here is equal to the probability that the event t happens in the interval intersect with the interval t larger than t, divided by the probability that capital T, so the event, happens after t. But if we take a look to this expression here, so to this interval, so the intersection between the first interval between t and dt, that is the smaller one here, and t larger than, capital T larger than t, so that the event is larger than t, then we see that the intersection between the gray part and the orange part is actually the orange one. So what's happened is that the probability that the event of failure happens in the interval, given that the component was working at the beginning of the interval, is equal to the probability that the event happens inside the interval, divided by the probability that the event happens after the beginning of the interval. So we can calculate the probability, and then we can then apply the substitution, because the upper part here is equal to f dt in dt. And the lower part here, the probability that the event happened after t, is actually the definition of the reliability. And starting from this, we can find other two interesting expressions that actually From this result, we can notice how, and maybe it was expected, that the probability of having a failure at the time t, given that it was working at the beginning of the interval of interest, can be seen as a discount rate on the reliability. So it can be seen as a reliability reduction in this second case, or can be seen as an unreliability increment for the first case. To better understand the difference between the failure rate and the probability of failure, let us consider a very simple example on a discrete time. So, the failure rate can be interpreted as the number of faults in a unit time. And the difference between lambda t and fdt is the fact that while fdt refers to the healthy population at time t equal to 0, so at the beginning of the time, lambda t refers to the healthy population at time t, so in the moment in which we are considering actually lambda. So, what does it mean? It means that we are considering a population that is smaller with respect to the one that was healthy at time t equal to 0. So here we have an example. So we have n components, actually 16 components, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, 16 components. And here there are 6 moments in time, 6 intervals, okay? And the length of the bar represents how many of those components failed in a certain moment. We mentioned we are considering discrete time intervals. So if we calculate the f, so the probability density function at time t equal to 3, this is the number of failure that we have here, 4, divided by the entire population, and 0, that is 16. On the opposite, if we consider the failure rate at 3, we have to count the number of components that fails in the interval 3, that is 4 as before, but we have to consider only the number of components that were healthy at the beginning of this interval, that is 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So lambda at the third interval is 4 divided by 11. So the failure rate in this case is 0.36. On the opposite, the probability density function is 0.25.